Hi friends, welcome to Circuit Tricks. In this PLL lecture series, I will try to cover all the topics about the PLL and finally I will show you how to design a PLL with an example. Let's start with the basics of the PLL. Circuits are in general analyzed using voltage, current and charge. In PLL, we deal with phase and frequency. PLL are used to generate the clock signals that are periodic in nature. So let's see briefly about phase, frequency and how they are related to each other. Periodic signal is the one that repeats the sequence of value exactly after a fixed length of time known as period. Here we can call this period as T. To find the value of the signal at any given instance of time, all we need to do is trace the point along the circle. Say at time t, the signal has a value p as shown here. From the radius of the circle and the angle it makes with the x-axis, that is theta, we can get the information about p. The y value of the signal can be found by taking r sin theta and x value of the signal can be found by taking r cos theta. Let us trace the points along the circle for every 30 degrees change in phase. We can see from here that the signal forms a sinusoidal waveform pattern with the amplitude equals to the radius r. Exactly, it reaches the amplitude when it shifts, the phase goes to 90 degrees. We can see that over the period of time the radius r remains constant, so the amplitude is insignificant for the case of PLL. Only the phase is changing with the time. The phase variation with respect to time in a separate graph. As we can see from here that the phase of the signal changes linearly over time and completes exactly 2 pi radians per period. Every period it gets repeated, so it exactly completes 2 pi radians. Now let me introduce another term called angular velocity. It is the measure of how fast the angular position of the signal changes with the time. Say for example, if d theta is the change in phase angle over a change in time called dt, then angular velocity is change in phase to change in time, which is d theta by dt. The same thing can be measured as a slope on this curve. The unit for this angular velocity is radian per second, and as we see from here, it completes exactly 2 pi radians over every period. So its value for periodic signal is 2 pi by t. So now we can introduce another term called frequency, which is a measure of number of cycles it completes over a second. So just by dividing the angular velocity by 2 pi, we can get the frequency. So frequency is 1 by t for the periodic signal and its units is hertz or cycles per second. With this understanding of the basic, let us start with the PLL. The essential element of the PLL is oscillator to generate the periodic signal. The symbol for the oscillator is shown here and the output is a signal with a frequency f out. Now let us see the basic operation of a simple oscillator. Consider a tank circuit where a capacitor is connected in parallel to a coil through a switch. Initially, the capacitor is charged with a positive charge on the top plate and negative charge at the bottom plate. Once the supply is removed and the switch is closed, the electron will try to flow through the coil towards the positive charge. The electromagnetic field created around the coil will oppose the flow of electrons, so the energy now gets stored in the form of magnetic field in the coil. As the more and more charges getting discharged from the capacitor, more and more magnetic field gets built up. Once all the charges are discharged from the capacitor, now all the energy is stored in the form of magnetic field. Now there is no electric field to support the flow of current, so the magnetic field start collapsing and electron move towards the top plate. Now more and more electron move towards the top plate and magnetic field start reducing. Gradually electric field starts building up and finally all the energy is stored in the form of electric field with the electron in the top plate now and positive charge at the bottom plate. Now the electron flows in the opposite direction and repeats the whole process of alternating between magnetic field and electric field. This process repeats for every cycle, and this way it sustains the oscillation. If we measure the current through this tank circuit, initially the current flows from top plate towards the bottom plate, and next half this current flows from bottom plate towards the top plate, and it repeats forever. Okay, so now we need to find out what is the frequency at which the circuit will oscillate. Okay, so if we have a tank circuit with the value of L as the coil and C as the capacitance, we can calculate the impedance of the tank using these two formulas. As we plot the impedance across frequencies sweeping from DC to very high value, we can find out that close to zero frequency, the capacitor is an open circuit, and at very high frequency, capacitor acts as a short circuit. Similarly, conversely, the inductor acts as a open circuit at very high frequencies, but it is a short circuit at the DC. So there is a frequency which we call it as FR or resonant frequency, where the impedance from the coil and the capacitor matches with each other. So here the both voltage and current will be in phase, and the circuit at this point is called tuned circuit. So now we can equate these two equations at this frequency as shown here, and rearranging this we can find out the resonant frequency value, which is 1 by 2 pi square root of LC. So this is the frequency at which the tank will oscillate. So this sustained oscillation is shown over here with the frequency FR equal to 1 by T. As the coils are realized using metal, they are associated with the parasitic resistance. So these resistors can be clubbed together with a value equal to Rp in parallel with L and C. Whenever current flows through the resistor, energy in the tank gets lost in the form of heat. As energy gradually leaks through these resistors, oscillation dies out over the period of time as shown here. Now let us see how to sustain the oscillation. By adding a negative resistance to the lossy tank circuit, the energy lost can be replenished. So what is a negative resistance? When the voltage across a resistor reduces, the current through it also reduces. But in the case of negative resistance, as the voltage reduces, the current through it increases. Let us see an example case. Here we have a design to realize a negative resistance. If the voltage V2 reduces, the gate voltage of transistor M2 also reduces, which in turn results in the reduced current of I2. As total current to support this circuit is equal to I, the current through M1 will increase. So, by using a positive feedback, we have realized a negative resistance. Now let us calculate the impedance, how much it will offer, looking through the output node. For that, we need to remove this current source and connect a voltage source at the output. The input impedance is calculated as the ratio of Vx over Ix. So if V2 is the voltage applied across M2, then it will generate a current Gm V2. And if V1 is the voltage across M1, it will generate a current equal to Gm into M1. Now we can see that Ix is the current which is flowing from positive point towards the negative point of the supply. So Ix will be equal to GmV2 and minus GmV1, because this is in the opposite direction. We also know that Vx is V2 minus V1. By rearranging these equations, we can find the value of input impedance as Rin equal to minus 2 by Gm. So now this circuit can be connected in parallel with the tank circuit, which will offer a negative resistance. By keeping the value of 2 over Gm less than or equal to Rp, we can replenish the energy lost every time. So This will sustain the oscillation. After adding negative resistance to this tank circuit will oscillate at resonant frequency, which is given by this equation. So here we can see that the frequency depends only on the values of L and C. But wafer to wafer manufacturing precise inductance and capacitance is not possible. So the center frequency would vary across the process corners. So in order to tune the center frequency, we will be adding a control circuitry as shown here. Here we have a variable capacitor which is connected in parallel with this C. So the center frequency will now be a function of total capacitance, which is the tank capacitor plus the varying capacitor. So now by varying this control voltage, we can change the capacitor as shown here. Now the VCO symbol is added with the input control pin as shown over here. If we plot input versus output like varying the control voltage, we will find out that the frequency increases. The slope or the change in output frequency to the change in input frequency is called gain of the VCO, and here we use this symbol kV. So thus we can write the input to output relationship as F out equal to kV times your input voltage. In general, PLL loops are analyzed either using frequency or phase. So here we will be using phase for analyzing the PLL. So we will convert this frequency to phase by integrating the angular velocity over time. So replacing this F out with the kV into Vc over T, we will be getting the output phase to input control voltage relationship. By taking a Laplace transform, we would be getting a transfer function. So this is the transfer function or the block diagram of the VCO with input as control voltage and output as the phase. Now we can see from the transfer function that it has a pole at the origin. So VCO is actually an integrator. Okay. So now we have an oscillator which can generate an output frequency and also can be controlled using a control voltage. So this is called voltage controlled oscillator or VCO. But the oscillation frequency drifts away over a period of time mainly because of the noise generated within the devices. So what we do is we use negative feedback technique to dynamically tune the control voltage and try to keep the output frequency constant. For this we need a reference clock which is very precise in frequency value. So for example, crystal oscillators can generate very precise and accurate frequency signals. Okay, so then the VCO frequency will be compared with the reference frequency, and the error what we get out of this comparison will be used to control the VCO oscillation frequency. Okay, so typically the reference frequency will be much smaller than the VCO frequency. Say for example, VCO frequency could be at 1 GHz, whereas the reference frequency may be of 100 MHz. In that case, we need a divider. For this example, we need divide by 10. Now let us see the basic operations of a divider. So the input for the divider is the VCO output frequency, and its output is the feedback clock or the clock for which will be used to compare the reference clock. Okay, so this is the expression for divider where 1 by n is the divider value. So it divides the VCO output frequency by n times. Generally we analyze the PLL in phase domain, so let's convert that into phase. So feedback phase is given by integrating the feedback frequency over a time. Okay, so now replacing this term with this term, we will be getting this expression. So since integration of f out of t dt is theta out of t dt, we can replace that with this. By taking the Laplace transform, we will be able to get the transfer function of this divider. So since 1 by n is not changing over the time, the Laplace transform also remains the same. So thus the transfer function of divider is 1 by n. So now we have a divider and the frequency of VCO now divided and matched exactly with the input reference frequency. Now we need a comparator to compare their phase and frequency alignment. Let's see a briefly a phase frequency comparator, or this is called phase frequency detector. So here we have a phase frequency detector which generates a error signal in terms of phase difference between the input and the feedback clock. So this is an example design of a phase frequency detector. So here we have two inputs, one is a reference clock and the other one is the feedback clock. Their phase and frequency will be compared and the error signal will be captured in theta e. So the output of the AND gate will reset these two flops. Let us assume that initial value of these two flops are 0. Consider a case where reference clock is leading the feedback clock. So first we will encounter a rising edge of the reference clock which will set the flop to high. So up will go high. It up signal will stay high until the feedback clock has a rising edge. This rising edge will toggle the down signal also to 1. Since these two inputs of the AND gates are 1, it will reset these two flops to 0. So the error signal which is calculated as a difference between the up and down signal will have a pulse as shown over here. So this will be repeated until these clocks are until the reference clock is leading the feedback clock. Here we can see that the phase difference between the reference clock and the feedback clock is captured in the pulse width, and we can also see that the direction of the pulse is a positive. So now consider the second case where reference clock is actually lagging behind the feedback clock. So here the feedback clock will have a rising edge first, which in turn trigger the down signal to high, and this down signal will stay high until the reference clock has a rising edge. Then the up signal will go high. So since both these signals are high, the AND gate will reset these two latches again back to 0. Now if we see this error signal, it has now a negative pulse. Okay, so the negative or positive of the pulse gives the information about whether the reference clock is lagging or leading the feedback clock, and the pulse width gives the information about how much it is leading or lagging each other. In case of both these clocks are aligned together, then both up and down signals are issued simultaneously, and reset of the flop also happens simultaneously. So essentially if you see the error signal which will remain always 0. Now let us plot the transfer function or the input-output relationship for the phase frequency detector. Here, when this reference clock is exactly aligned with the feedback clock, the output value is always 0, and that can be represented as a 0 over here in the transfer function. When this feedback clock is lagging the reference clock by 1/4 of a period, then we will be generating a pulse which is of a having a width equal to 1/4 of the period. So if we take an average, we will be getting a 1/4 of the maximum value, which can be represented over here. Similarly, when it is lagging by half, then we can represent this by over here, and when they are lagging by 3/4, then the value will be 3/4 of the maximum. When exactly they are 2 pi, then we will reach the maximum value at the output. In this case, it can even compare this as a previous value of the feedback clock, and it will have a discontinuity over here. Now consider the case where your feedback clock is leading the reference clock. So the whole process repeats in the reverse direction with the voltage changing from 0 towards minus maximum voltage. In this case, it is minus 1 volt. When the feedback clock lags the reference clock or leading the reference clock by complete 2 pi radians or 1 cycle, then it will have again a discontinuity as shown over here. So the plot beyond 2 pi, it will start repeating as shown over here. So if we take the slope, that will give the gain of the phase frequency detector. So we can see here that it is changing linearly from minus 1 to 1 volt for radians minus 2 pi to 2 pi change in the input difference. So the slope, if we calculate, that would be equal to 1 by 2 pi. So now the transfer function can be represented as shown over here. So we have a phase of a reference clock and we have a phase of the feedback clock. The difference is generated as a phase error over here, which is getting multiplied by the gain of the phase frequency detector, which is 1 by 2 pi, and gives me the output. Okay, so now we have the phase frequency detector which compares the VCO frequency and phase with the reference frequency and phase. Our ultimate goal is to make this error a zero. So we need to introduce a circuit over here which essentially gives me a constant voltage for zero input and gives me an increasing voltage for positive error and decreasing voltage for negative error. So what I mean is when I have a positive error, I need to pump up this voltage in order to increase the frequency and phase of the VCO. And similarly, when I have a negative error, I need to reduce this voltage in order to reduce the frequency of the VCO. So I need to add an integrator because integrator gives me output 0 only when the input is 0. If the input is positive constant value, then output will be a ramp positive with a positive slope for an integrator, and if the input is a negative constant value, then the output will be a ramp with a negative slope. Now let us understand how to implement an integrator. So here we will be using a charge pump based integrator. So here we have two current sources of equal value connected as shown over here. When this switch is closed, this current will charge this capacitor with a slope equal to ICP divided by C, and this is having a positive slope. When this switch is closed and this switch is open, this will discharge the uh, charges from the capacitor with a negative slope of ICP by C. So this acts as an integrator. So when both the switches are open, it will be constant, and when both the switches are closed, then all the current from this current source will go through this current source, and in this case also the voltage remains constant. So this charge pump based integrator can be used with the phase frequency detector. So let us see the combination of phase frequency detector and charge pump based integrator. So here we have the phase frequency detector whose output, this up signal and down signal, are connected to the charge pump. So let us consider the same cases where the reference clock is leading the feedback clock. When up signal is generated, this switch is closed and this will charge this capacitor. So the VC will increase until this up is on. Moment this down is on or both are open, then it will remain constant, and this will repeat as shown over here. In the case of reference clock lagging behind the feedback clock, your down signal will be issued first and it will discharge the value from the capacitor and the voltage will start decreasing. Moment these both switches are open, here it will maintain the constant voltage. And this process repeats for every cycle. Here we can see for the case when they are aligned, we never get either up signal or down signal, so the voltage output remains constant. Now let now let us analyze the PFD charge pump combination to derive the transfer function. So here we can see that the capacitor is charged only during the time when the up signal is high, and remaining time the output voltage does not change. So this is a discrete system. A system can be analyzed only if it is perfectly linear. So we can linearize this system by assuming that the same amount of charge is distributed over the entire period T. Okay, so now we can calculate the charge deposited into the capacitor by taking the area under this red color rectangle. So if delta T is the phase difference and ICP is the charge pump current, then change in charge is given by ICP into delta T. Now we have to replace this delta T with theta E, which is in terms of phase. If delta T is over a period of time T, then theta E is over 2 pi radians. So now replacing this delta T, we will be getting the total charge injected into the capacitor. We distribute this charge over the entire period T. So we have to calculate the average current, we have to divide this charge by T. So then we have the average current for every cycle. By integrating this average current with respect to capacitor or with respect to time with a slope of 1 by C, we will be getting the control voltage. So this is the expression for the control voltage, which is 1 over C integration of IT dt. So replacing this ITTT with average current, we get ICP by 2 pi C integral theta ET dt. So by taking the Laplace transform of this control voltage, we can get the transfer function. So the transfer function is ICP over 2 pi Cs. So now we have all the essential elements of the PLL. We have VCO which generates the periodic signal, and we have a divider which matches the frequency of VCO output to the reference clock. We have phase frequency detector which compares the VCO frequency with the reference frequency and generates the error signal, and we have an integrator which either ramps up or ramps down the control voltage according to the error signal. So when the phase, for example, of the VCO is lagging the reference clock, then the phase detector will issue a up signal. Then the control voltage will increase until the phase error becomes zero. Thus, by using a negative feedback, we have realized a PLL which generates the constant phase and frequency output signal. We can replace each block with its transfer function as shown over here. So 2 pi kV divided by S is the oscillator transfer function, and 1 by N is the divider transfer function, and ICP by 2 pi CS is the PFD charge pump combination transfer function. So here we can see that we have two integrator, one because of this charge pump capacitor combination, and another integrator because of the VCO. So we need to understand whether the system will remain stable or not. So for that we need to thoroughly analyze the slope, so which will be covered in my next lecture. So thus in this lecture we have understood the basic operating principles of the PLL. So thanks a lot for watching this video, and if you like it, please hit the like button. Also please don't forget to subscribe my channel. If you have any comments, please add it below so that will improve my subsequent video postings. Thanks a lot once again for watching this video.